High on a dry volcanic plateau in the northern Andes, the Atacama Desert lies freezing beneath the midnight sky. The air at 5,000 meters above sea level is thin, still, and almost completely stripped of atmospheric moisture. There is no sound here, no movement of trees, no distant rumble of human machinery. A lone observer stands on the barren, frost-shattered gravel and tilts their head toward the zenith. Directly overhead, surrounded by the pale, luminous dust lanes of the Milky Way, burns a single bright star. It is Deneb, the blue-white supergiant, marking the tail of the great celestial swan. To the bare human eye, it is merely a steady, diamond-cold point of light, piercing the dark. Yet in this quiet moment of observation, an astonishing physical event is taking place. Across the immense, freezing gulf of interstellar space, something has just arrived. It has crossed 2,600 light-years of absolute vacuum without pausing, without swerving, and without losing its identity. It pours down through the thin desert atmosphere, passes through the crystalline lens of the observer's eye, and slams into a microscopic patch of light-sensitive tissue at the back of the retina. What is this messenger? We call it starlight, and our intuition tells us it is a continuous stream, a smooth, unbroken river of illumination, bridging the distance between the star and the human eye. But our intuition is completely wrong. Light is not a smooth, continuous fluid. It is a rain of discrete, indivisible entities. It is a downpour of subatomic ghosts, each one a tiny packet of pure energy called a photon. To understand the photon is to pull at the very fabric of reality. It is the fundamental particle of electromagnetism, the entity that carries the warmth of the sun, the colors of the world, the radio signals between continents, and the faint, whispering afterglow of the Big Bang itself. Yet, the closer we examine this particle, the more our everyday understanding of the universe begins to unravel. The photon has no physical mass whatsoever. It is born in violent subatomic collisions and exists only at the absolute speed limit of the cosmos. To a photon, the concept of time does not exist. Its birth in the core of a dying star and its destruction against the human retina occur at the exact same indivisible instant. It behaves like a solid bullet of energy when it strikes matter, yet it ripples through space like a spreading wave on a pond, seemingly capable of being in many places at once until the universe forces it to make a choice. This is the story of how humanity uncovered the true nature of light, and why the simplest thing we experience every day, the act of seeing, rests upon the strangest rules in all of physics. To understand how radical the modern concept of the photon truly is, we must look backward to how humanity first attempted to explain the miracle of vision. For thousands of years, the relationship between the eye and the universe was a matter of profound philosophical confusion. In ancient Greece, scholars like Empedocles and Euclid believed that human eyes were active projectors. They imagined that visual rays streamed outward from our pupils like invisible tentacles or the beams of lanterns, reaching across space to touch the objects around us. In this ancient view, we saw the night sky because our eyes actively brushed against the stars. It was not until the 11th century that the scholar Ibn al-Haytham, pronounced Ibn al-Haytham, working in Cairo, systematically destroyed the visual ray hypothesis. He pointed out a simple, painful fact. If you stare directly at the sun, your eyes burn. If vision depended on rays reaching outward from us to the sun, looking at a bright object should cause no more physical discomfort than looking at a dark stone. He realized that light must be an independent physical entity that originates from external sources, bounces off the objects in the world, and travels through space to enter our pupils from the outside. Light was not something we did. Light was something that happened to us. Once light was recognized as an independent traveler moving through the void, a new and bitter controversy erupted. What was this traveler made of? In the late 17th century, Isaac Newton turned his formidable intellect to the problem of light. In his darkened rooms at Trinity College, Newton bored a tiny hole in his window shutter, allowing a single shaft of sunlight to pierce the gloom. He placed a glass prism in the path of the beam and watched as the white light fanned out into a brilliant rainbow of red, yellow, green, and violet on his wall. When he placed a second inverted prism in the path of that rainbow, the colors merged back together to form a spot of pure white light. Newton concluded that light was a stream of material projectiles. He proposed the corpuscular theory, arguing that light consisted of swarms of tiny, hard, indivisible bullets flying through space in straight lines. His reasoning seemed rock solid to the mechanical minds of the era. A ball thrown across a room travels in a straight line, bouncing off walls at predictable angles, just as a beam of light reflects off a mirror. Furthermore, solid objects cast sharp, distinct shadows. If light were a fluid or a spreading vibration, Newton argued, it would curve around corners and flood into the shadows, just as ocean waves swirl around the base of a rock. Since sharp shadows existed, light had to be made of straight-flying bullets. Yet even as Newton dominated the scientific landscape, a quiet counter-revolution was brewing across the English Channel. The Dutch mathematician Christian Huygens, pronounced Christian Huygens, looked at the world and saw vibrations. Huygens watched ripples spreading across the surface of a pond when two stones were dropped into the water at the same time. He noticed that when the expanding circles of water ripples collided, they did not smash into each other and scatter like billiard balls. Instead, the waves passed straight through one another without losing their shape or their speed. Huygens realized that beams of light behaved in the exact same way. When two people stand in a dark room and shine two lanterns so that their beams cross in midair, the beams do not collide. They do not scatter off each other like streams of bullets. They pass through one another in total silence and continue on their way undisturbed. To Huygens, this was absolute proof that light could not be a stream of solid particles. Light had to be a wave, a mechanical pulse rippling through an invisible ocean. For over a century, the scientific world remained deeply divided between Newton's flying bullets and Huygens's spreading waves. But at the dawn of the 19th century, an English physician and polymath named Thomas Young devised an experiment of such breathtaking simplicity that it seemed to settle the debate forever. Young allowed a narrow beam of sunlight to fall onto a screen containing two tiny, parallel vertical slits placed close together. He then set up a viewing screen behind the slits to catch the light that passed through. If Newton's particle theory was correct, the light bullets passing through the two slits would simply paint two bright parallel stripes on the viewing screen, like sand poured through two cracks in a floor. That is not what Young saw. When the light passed through the two slits, it did not form two bright stripes. Instead, it spread out and painted an intricate zebra-like pattern of alternating bright and dark vertical bands across the entire viewing screen. There were bright stripes where there should have been shadow, and dark regions right in the center where the light should have been brightest. This phenomenon is called interference, which is the pattern created when two or more overlapping waves combine to reinforce or cancel each other out. Picture those two stones dropped into the pond again. As the two sets of circular ripples expand and overlap, there are places where the high crest of one wave meets the high crest of another. When this happens, the water piles up twice as high, creating a bright band of reinforcement. But there are also places where the high crest of one wave arrives at the exact same moment as the low trough of the other wave. Here, the upward pull of the crest cancels out the downward pull of the trough. The water is forced flat, leaving a region of absolute stillness. Thomas Young had discovered dead, calm water in a sea of light. The dark bands on his screen were places where the light waves emerging from the left slit arrived exactly out of step with the light waves emerging from the right slit, completely destroying one another. Particle bullets could never cancel each other out to create darkness. Only waves could do that. With Young's double-slit demonstration, the particle theory of light was pronounced dead. The 19th century belonged entirely to the wave. As the wave theory triumphed, a profound mystery emerged to challenge the greatest minds of physics. A wave is not a thing in itself. A wave is something that a medium does. When you hear a bell ring, sound waves are traveling to your ear, but those sound waves are merely rhythmic compressions and rarefactions of air molecules. Without air, there is no sound. When an ocean wave crashes on the beach, it is the water that is moving. If light is a wave, what is waving? How can light travel from the sun to the earth across millions of miles of empty, airless space? To solve this riddle, 19th century physicists invented a hypothetical cosmic substance called the luminiferous ether, pronounced ether, an invisible, weightless, infinitely rigid, yet perfectly fluid medium supposed to permeate the entire universe. They believed that stars and planets swam through this silent ocean, and that light was simply a mechanical vibration shivering through the ether, just as sound shivers through the atmosphere. Then came James Clerk Maxwell. In the 1860s, this brilliant Scottish physicist set out to unify the seemingly separate phenomena of electricity and magnetism. Through brilliant mathematical deduction, Maxwell discovered that electricity and magnetism were locked in an eternal, intimate dance. He found that a moving electrical charge creates a magnetic field around itself. More importantly, he proved that a rapidly changing magnetic field creates a new electric field, which in turn creates a new magnetic field over and over again. Maxwell realized that if you shook an electrical charge back forth rapidly enough, this leapfrogging cycle of electricity and magnetism would detach from the source and go hurtling out into empty space as a self-sustaining disturbance. He calculated the speed at which this electromagnetic wave would travel through the void. The number that dropped out of his equations was astounding. The calculated speed of this electromagnetic wave was roughly 300,000 kilometers per second, which is about 186,000 miles per second. This number was already well known to astronomers. It was the experimentally measured speed of light. In one of the greatest intellectual leaps in human history, Maxwell realized that this was not a coincidence. Light was not a mechanical vibration of some mysterious fluid ether. Light was an electromagnetic wave. It was a rapid, self-propagating ripple in the electromagnetic field that permeates all of existence. Maxwell revealed that visible light, the colors from deep red to violet that our human eyes can detect, is merely one tiny, narrow octave on an immense, unseen keyboard of cosmic radiation. If you shake an electrical charge slowly, you produce long, gentle radio waves. If you shake it faster, you get microwaves, then infrared warmth, then visible light, then ultraviolet rays, X-rays, and finally, the devastating ultra-fast vibrations of gamma rays. They are all the exact same physical phenomenon, differing only in their wavelength, which is the physical distance between the crest of one wave and the crest of the next. With Maxwell's triumph, classical physics seemed complete. Light was definitively understood as an electromagnetic wave. Yet the ghost of the ether still haunted the laboratories of the world. Even if light was an electromagnetic wave, scientists still believed that the electromagnetic field must be anchored in the physical ocean of the ether. In the year 1887, two American physicists, Albert Michelson, pronounced Michelson, and Edward Morley, set out to detect the Earth's motion through this ocean. They built a massive, incredibly sensitive optical instrument called an interferometer, a device designed to split a beam of light into two perpendicular paths, send them bouncing off mirrors, and then recombine them to see if one beam took longer to return than the other. They floated their stone table in a pool of liquid mercury in a basement in Ohio to eliminate every vibration from the outside world. Their logic was simple. As the Earth orbits the Sun at roughly 30 kilometers per second, our planet must be rushing through the static ocean of the ether, creating a constant physical wind of ether blowing across our instruments. Therefore, a beam of light traveling directly into the headwind of the ether should move slightly slower than a beam of light traveling perpendicular to it, just as a swimmer moves slower against a river current. Michelson and Morley rotated their instrument, waiting for the interference fringes of their light beams to shift and reveal the absolute speed of the Earth through the cosmos. Nothing happened. No matter which way they turned their apparatus, no matter the time of day or the season of the year, the speed of light remained completely, stubbornly unchanged. There was no wind. There was no drift. The light beams always traveled at the exact same velocity, 300,000 kilometers per second. The result was a total zero. The scientific community was thrown into confusion. How could the speed of light be constant for every observer, regardless of how fast the observer was moving toward or away from the light source? If you run toward a thrown baseball, the ball hits you with a higher combined speed. But if you run toward an incoming beam of light, its measured speed does not increase by even a fraction of a millimeter per second. It hits you at 300,000 kilometers per second. If you jump into a spaceship and flee away from that same light beam at half the speed of light, the beam does not catch up to you at half speed. It still overtakes you at exactly 300,000 kilometers per second. The invisible ocean of the ether did not exist. Light needed no medium to carry it. It traveled through true, empty vacuum, obeying rules that broke the common-sense mechanics of the world. Just as physicists were reeling from the failure to find the ether, a second, even more terrifying crisis began to emerge from a seemingly mundane corner of experimental physics: the glow of hot objects. Every physical object in the universe emits light. When you heat a horseshoe in a blacksmith's furnace, it begins to glow with a deep, dull red. As it gets hotter, the color shifts to bright orange, then yellow, and finally, at extreme temperatures, it blazes with a searing blue-white brilliance. Physicists called this phenomenon blackbody radiation, referring to the thermal light emitted by an idealized, perfectly absorbing object as it warms up. According to the laws of classical wave theory, calculating the exact colors and intensities of this thermal glow should have been straightforward. Scientists treated the walls of a hot oven as a collection of microscopic atomic oscillators, little electrical pendulums vibrating at every possible frequency and pumping electromagnetic waves into the cavity. But when they used Maxwell's wave equations to calculate how much total energy a hot object should radiate, the mathematics produced a catastrophe. Classical wave theory dictated that there were infinitely more ways for an object to vibrate at very short, high frequencies than at long, low frequencies. This meant that any warm object, even a cup of lukewarm tea or the human body, should instantly dump all of its thermal energy into the highest possible frequencies. The equations predicted that every warm object in the universe should instantly emit an infinite blast of blinding ultraviolet light, X-rays, and gamma rays, freezing itself to absolute zero in a fraction of a second. This absurd mathematical prediction became known in the history of science as the ultraviolet catastrophe. Classical physics was predicting that simple heat was impossible, and that the universe should destroy itself in an infinite flash of high-frequency radiation. Clearly, something was deeply, fundamentally wrong with our understanding of light. In the final weeks of the year 1900, a German theoretical physicist named Max Planck, pronounced Planck, sat at his desk in Berlin, desperately attempting to fix the mathematics of the hot oven. Planck was a staunch conservative in science. He had no desire to overthrow the established laws of physics. He simply wanted to find a mathematical formula that matched the actual experimental measurements of glowing objects. Through a process of trial and error, Planck stumbled upon an equation that described the exact curve of thermal radiation with miraculous precision. But to make the mathematics work, Planck had to introduce a strange, artificial restriction into his calculations. He had to assume that the microscopic atomic oscillators in the walls of the oven could not absorb or emit thermal energy in a smooth, continuous stream. Instead, he forced the energy to be divided into discrete, indivisible packets, like counting money in whole coins rather than continuous fluid amounts. Planck called these indivisible packets of energy quanta, from the Latin word meaning how much. He calculated that the amount of energy trapped inside each packet was directly proportional to the frequency of the vibration, a relationship governed by a tiny, fundamental number that would come to be known as Planck's constant. To Max Planck, this assumption was simply an act of mathematical desperation. He did not believe that energy or light was actually broken up into little physical bullets in the real world. He thought the quantum was merely a temporary accounting trick, a mathematical illusion that would eventually be explained away by classical wave mechanics. It would take a 26-year-old patent clerk in Bern, Switzerland, to look at Planck's accounting trick and realize that it was the absolute physical truth of the universe. In the spring of 1905, Albert Einstein published a paper that would eventually win him the Nobel Prize in physics. Einstein turned his attention to a mysterious scientific puzzle known as the photoelectric effect, a phenomenon where shining light onto a clean metal surface knocks electrons out of the metal, creating a detectable electric current. For decades, experimental physicists had been baffling over how this electrical current behaved. According to classical wave theory, light was a continuous, spreading ripple of energy. If you shone a very faint red light onto a metal plate, the ocean of waves should gently wash over the atoms. It might take several minutes or even hours for a single electron to soak up enough energy from the gentle ripples to break free from its atomic bonds and fly out of the metal. Furthermore, if you turned up the brightness of that red light, making the waves taller and more powerful, the electrons should be violently blasted out of the metal at much higher speeds. When the experiments were run in the dark rooms of Europe, the results defied every prediction of wave theory. When scientists shone intense, blindingly bright red light onto the metal plate, nothing happened. Not a single electron was ejected. They could leave the bright red light on for hours, and the metal remained completely dead. Yet, the very instant they shone even the faintest, dimmest beam of ultraviolet light onto that same metal plate, electrons instantly leaped out of the surface without a microsecond of delay. What was even more baffling was that turning up the brightness of the ultraviolet light did not make the escaping electrons fly out any faster. It merely increased the number of electrons jumping out of the metal. Einstein looked at this experimental chaos and saw the simple, radical truth. Classical wave theory was failing because light does not travel through space as a continuous, spreading wave. Einstein proposed that light itself is physically quantized. A beam of light is not a smooth river. It is a hail of individual, localized bullets of energy traveling through the void. In 1926, the physical chemist Gilbert Lewis would give these energy packets the permanent name we use today, photons. With Einstein's quantum leap, the photoelectric mystery evaporated into simple mechanical clarity. Think of the electrons trapped in the metal plate as balls sitting at the bottom of a steep well. To knock a ball out of the well, you must hit it with a single projectile that possesses a minimum amount of kick, because the energy of a photon is directly tied to its frequency. Color is literally a measure of subatomic impact. A red photon has a low frequency and a long wavelength. It carries very little energy. Shining a blindingly bright red light onto the metal is simply firing trillions of tiny, slow-moving ping-pong balls at the trapped electrons. No individual ping-pong ball has enough kick to dislodge an electron from the well. Since an electron can only absorb one photon at a time, firing a trillion weak photons at it does nothing. The electron simply absorbs the tiny impact, warms up slightly, and stays trapped. An ultraviolet photon, on the other hand, vibrates at a much higher frequency. It is a subatomic bullet of compressed energy. Even if the ultraviolet light is turned down so low that only a few photons are fired per second, every single ultraviolet photon hits like a rifle bullet. The instant one of these high-energy photons collides with an electron, it transfers its entire packet of energy in a single, clean strike, violently ejecting the electron from the metal instantly. Increasing the brightness of the light merely fires more rifle bullets per second, knocking out more electrons. But each individual electron flies away with the exact same speed, dictated entirely by the energy of the single photon that struck it. With Einstein's brilliant synthesis, the old 18th century particle theory of light had risen from the grave, reborn in a radical quantum form. Yet this victory did not destroy the wave theory. Thomas Young's interference stripes and Maxwell's equations were still absolute verifiable facts. Light undeniably rippled like a wave in space, yet it undeniably hit like a particle when it collided with matter. The universe was forcing humanity to confront a deep, uncomfortable paradox. The photon was not simply a particle, nor was it simply a wave. It was something entirely new, an entity that defied the everyday language of human beings. What, then, is a photon? If we could strip away the limitations of our human senses and examine this subatomic entity as it crosses the universe, what kind of object would we find? To begin with, we must abandon our everyday understanding of mass. Every object we interact with in daily life, from a mountain to a grain of sand to the electrons orbiting an atom, possesses physical weight, a property physicists call rest mass. Rest mass is the inherent resistance of an object to being pushed. It is the amount of matter and energy packed into a particle when it is sitting completely still. A photon has an absolute rest mass of 0. There is no physical stuff inside a photon, no solid kernel of matter waiting to be weighed on a scale. It is a pure, localized bundle of electromagnetic field energy. This total absence of mass dictates the most profound and violent rule of the photon's existence. It can never, ever be still. In our universe, any entity with 0 rest mass has no choice in its velocity. From the exact fraction of a microsecond it is born, a photon must instantly move at the maximum speed limit of reality, 300,000 kilometers per second in a vacuum. You cannot push a photon to make it go faster, and you cannot brake a photon to slow it down. A car accelerating on a highway must smoothly transition from 30 kilometers an hour to 60, gaining speed over time. A photon does not accelerate. The moment an electron drops to a lower energy level in an atom or a nuclear fire fuses hydrogen in a star, the newly created photon leaps into existence already traveling at the absolute speed of light. It knows no other pace. Yet despite having no rest mass whatsoever, the photon is not a weightless ghost without physical punch. It possesses momentum, the mechanical drive that allows a moving object to strike another and transfer kinetic energy. How can something with no mass carry physical momentum? In the year 1923, the American physicist Arthur Compton directed a beam of high-energy X-ray photons at a target of carbon atoms. If X-rays were purely spreading waves, they would simply wash over the electrons in the carbon atoms, causing them to oscillate and radiate new waves at the exact same frequency. But when Compton measured the scattered X-rays bouncing off the target, he discovered that the light had changed color. The scattered photons had shifted to longer wavelengths. They had lost physical energy in the collision. At the exact same time, electrons were being knocked out of the carbon atoms at high speeds, recoiling like billiard balls that had just been struck by a solid cue ball. Compton had captured a direct subatomic collision. The massless photon had struck the electron with real mechanical force, transferring some of its own momentum to the electron and bouncing away with less energy than it had before the impact. This phenomenon, known today as Compton scattering, proved beyond any lingering doubt that photons carry momentum. The pressure of sunlight is not a metaphor, it is a literal mechanical push exerted by trillions of massless energy packets raining down on a surface. This radiation pressure is the invisible broom that sweeps through the solar system, blowing the delicate, glowing gas tails of comets outward and away from the sun. It is a physical force so reliable that engineers can design giant, mirror-bright solar sails, allowing future spacecraft to silently surf across the emptiness of deep space, accelerated to tremendous speeds entirely by the relentless bombardment of solar photons. We now see the photon as a robust, energetic packet capable of physically punching electrons across a room. Yet the moment we try to pin down its location in space, the ghost of the wave returns to haunt us with a vengeance. Imagine we rebuild Thomas Young's famous double-slit experiment in a modern laboratory. We set up our barrier with two narrow slits, and behind it we place an ultra-sensitive digital detector screen capable of registering the impact of a single subatomic particle. But this time we do not flood the apparatus with a continuous beam of sunlight. Instead, we use an advanced laser and a series of dark filters to dial the intensity of the light down so low that our source emits only one single photon every second. One individual photon leaves the laser. It travels through the dark, silent vacuum of the experimental chamber toward the barrier containing the two slits. A fraction of a microsecond later, a tiny, crisp spark of light flashes on the digital detector screen. A single dot appears. It is a precise, localized impact, looking exactly like a microscopic bullet hitting a target. We wait a second. A second photon leaves the laser, flies through the chamber, and strikes the screen. Another tiny, localized dot appears, landing in a different spot than the first. We let the experiment run, watching as the detector records the arrival of individual photons, one by one, spaced out over minutes and hours. Each impact is a discrete, point-like particle event. At first, the dots appear to be scattered at random across the screen. But as hundreds, then thousands, and finally tens of thousands of individual photon impacts accumulate on the display, a miraculous and terrifying picture begins to assemble before our eyes. The dots do not form two simple, bright stripes behind the two slits. Instead, the accumulation of thousands of individual, solid, bullet impacts builds up the exact same alternating interference pattern of bright and dark zebra bands that Thomas Young saw with continuous sunlight. Pause for a moment to grasp the impossibility of what has just occurred. Every single photon in this experiment traveled through the apparatus completely alone. There were no other photons in the chamber for it to collide with, no other waves to push or pull it off course. Yet, over time, the individual particles landed only in the bright interference zones, completely avoiding the dark bands where waves cancel out. How could a single, solitary particle know about the interference pattern? How could an indivisible bullet of light avoid the dark stripes unless it somehow knew the precise distance between the two slits? There is only one logical conclusion, and it shatters our classical view of reality. The single photon must have interfered with itself. While the photon was in flight between the laser and the detector screen, it did not exist as a tiny, solid marble traveling along a single, well-defined path. Instead, during its journey, the photon existed as a spreading wave of probability, a mathematical entity that quantum physicists call the wave function. This probability wave represents the likelihood of finding the photon at any given point in space. When this wave of potentiality reached the barrier, it did not choose one slit or the other. The wave function passed through both slits simultaneously. The ripple emerging from the left slit overlapped and interfered with the ripple emerging from the right slit, creating complex peaks and valleys of probability in the empty space behind the barrier. Where the two probability waves reinforced each other, the odds of the photon existing were high. Where the two probability waves canceled each other out, the odds of the photon existing dropped to absolute zero. Yet the photon does not land as a smeared-out wave. The very instant this spreading, ghost-like probability wave touches the detector screen, a profound quantum event takes place. The wave function collapses. In less than the blink of an eye, the spreading ripple of potentiality vanishes from everywhere else in the universe and condenses into a single, concrete, localized point of physical reality. The act of measurement, the physical interaction between the photon and the atoms of the screen, forces the quantum probability wave to choose a location, leaving behind a single, solid spark of light. The photon is neither a classical particle nor a classical wave. It is a quantum object. It travels as an expanding wave of possibilities, exploring every available path through the universe simultaneously, yet it is always absorbed and destroyed as a single, localized particle of absolute reality. If the dual nature of the photon seems to violate common sense, its relationship with time and space introduces us to an even deeper level of cosmic strangeness. To understand what existence looks like from the viewpoint of a photon, we must turn to Albert Einstein's 1905 theory of special relativity. Einstein realized that space and time are not absolute rigid background frameworks where events simply play out. Instead, they are deeply linked together into a single, flexible fabric called space-time. And the appearance of this fabric changes depending on how fast you are moving. One of the most famous consequences of relativity is a phenomenon called time dilation. Put simply, the faster an object moves through space, the slower its internal clock ticks relative to a stationary observer watching from the outside. Imagine an astronaut boarding a spaceship and accelerating out into the solar system. If the ship reaches 90% of the speed of light, an observer on Earth using a powerful telescope would see the astronaut's clock ticking much slower than their own. If the astronaut pushed the engines even harder, reaching 99.9% of the speed of light, the slowing of time would become extreme. A journey that takes 10 years from the perspective of people waiting on Earth might feel like only a few weeks to the astronaut inside the spacecraft. At the same time, a second relativistic effect called length contraction takes over. To the high-speed astronaut, the physical distance of the universe ahead of them actually shrinks along the direction of travel. Space itself compresses, making the journey shorter. Now, let us take Einstein's equations and push them to the absolute ultimate limit. What happens to time and space when an object reaches 100% of the speed of light? For an everyday object with mass, reaching the speed of light is mathematically impossible. It would require an infinite amount of energy. But our friend the photon is massless. It never moves at any other velocity. It is permanently locked at exactly 100% of the speed of light. When we plug the velocity of a photon into Einstein's time dilation equations, the mathematical denominator drops to zero. Time slowing down does not just become extreme. Time dilation becomes infinite. For any particle traveling at the exact speed of light, the ticking of the clock slows to an absolute, permanent stop. Consider what this means for a photon traveling across the deepest chasms of the universe. Imagine a telescope capturing a single photon of light that originated in the Andromeda galaxy, located 2,500,000 light-years away from Earth. To the human astronomers standing on our planet, that tiny packet of energy spent 2.5 million years crossing the freezing dark emptiness of intergalactic space. Entire human civilizations rose and fell, ice ages covered and retreated from the continents, and millions of generations of life lived and died on Earth while that photon was silently in flight. But let us adopt the subjective point of view of the photon itself. How much time elapsed on its watch? Zero. Because the photon travels at the speed of light, it experiences literally no passage of time whatsoever. The concept of duration does not exist for electromagnetic radiation. To the Andromeda photon, the exact moment of its creation inside the fiery atmosphere of a distant star and the exact moment of its destruction against the silver mirror of an earthly telescope occur at precisely the same indivisible instant. It does not age by a single microsecond. Whether a photon travels across a laboratory room or across 13 billion years of cosmic expansion from the edge of the observable universe, its internal clock never ticks even once. Furthermore, because of relativistic length contraction, the universe shrinks around the traveling light beam. At the speed of light, all physical distance along the axis of travel contracts to absolute zero. From the intrinsic viewpoint of the photon, the universe is infinitely flat. There is no gulf of space between the star in Andromeda and the lens of our telescope. To the photon, the star and the telescope mirror are pressed directly against one another, physically touching in a dimensionless point of absolute now. We look up at the night sky and see a vast historic tapestry of ancient light, a cosmos stretching across unimaginable oceans of space and time. Yet to the photons carrying that information to our eyes, the universe is a timeless instant where birth and death are unified in a single spark. Where do these timeless, massless messengers come from, and how do they make their way across the cosmos to reach our instruments? To answer this, let us trace the remarkable biography of a single solar photon, born in the closest stellar forge to our home, the core of the Sun. Our journey begins at the very center of our solar system, 1,500,000 kilometers beneath the visible surface of the Sun. Here, in the solar core, conditions are almost beyond human comprehension. The temperature blazes at 15 million degrees Celsius, and the crushing weight of the entire star presses inward with a pressure 260 billion times greater than the atmosphere of Earth. Under this unimaginable physical violence, atoms cannot hold on to their electrons. The core is a dense, boiling soup of ionized plasma, a chaotic sea of stripped proton nuclei and free-floating electrons. In this raging furnace, protons are slammed together with such tremendous kinetic force that they overcome their natural electrical repulsion and fuse together to form helium nuclei. This process is called thermonuclear fusion. Every time 4 hydrogen protons fuse to create a single helium nucleus, a tiny fraction of their combined mass, about 0.7%, vanishes. But mass cannot simply disappear. Obeying Einstein's famous equivalence principle, where energy equals mass multiplied by the speed of light squared, that missing matter is instantaneously converted into pure, unadulterated energy. This energy erupts into the plasma as a pair of ultra-high-frequency, lethal gamma-ray photons. Our newly minted gamma-ray photon leaps away from the site of the nuclear collision, moving at its mandatory speed of 300,000 kilometers per second. Its journey to freedom has begun. If the sun were empty space, our photon would race from the center of the star to the outer surface in just 2 seconds. But the core of the sun is not empty space. It is packed so densely with matter that a piece of solar core the size of a dice would weigh as much as a heavy bar of lead. Before our photon can travel even a fraction of a millimeter, it slams headlong into a free electron. The electron absorbs the high-energy photon, shudders with the impact, and instantly re-emits a brand new photon. However, this new photon is fired off in a completely random direction, and in the chaos of the collision, it loses a small amount of its energy. A microsecond later, this new photon travels another microscopic distance before slamming into another proton or electron, where it is absorbed and re-emitted yet again in another random direction. This frantic, staggering journey is known to physicists as a random walk. The photon is trapped in a cosmic pinball machine of unimaginable density, bouncing back and forth, left and right, inward and outward, trillions upon trillions of times every second. With every bounce, the photon loses a little bit of its high-frequency punch, slowly degrading from a violent gamma ray into a slightly longer X-ray, and then into an extreme ultraviolet wave. Because the direction of every bounce is completely accidental, the photon makes upward progress toward the surface of the sun at an agonizingly slow pace. It may spend years caught in a single cubic meter of plasma, bouncing back and forth billions of times without moving an inch closer to freedom. Calculations show that while it takes light only 2 seconds to cover the distance of the solar radius in a vacuum, a single packet of energy requires an average of 100,000 years just to struggle through the dense, boiling layers of the solar interior. Think about the implications of this immense delay. The warm sunlight hitting your face on a bright summer afternoon is not new energy. The thermonuclear reaction that created the energy warming your skin occurred deep inside the sun 100 centuries ago, while human beings on Earth were still painting animals on cave walls and carving tools out of stone. That energy has spent the entire history of human civilization fighting its way out of the solar core. Finally, after 100 millenniums of random collisions, our worn-down photon reaches the outer boundary of the Sun, a thin, transparent layer called the photosphere. Here, the density of the plasma drops off dramatically. The fog lifts. For the first time since its birth, the photon finds empty space ahead of it. By now, its energy has been degraded so significantly by trillions of subatomic collisions that it is no longer an X-ray. It has stretched out into a gentle, yellow-green wavelength of visible light, vibrating at roughly 500 trillion times a second. It leaps away from the solar photosphere at 300,000 kilometers per second, leaving the Sun behind forever. Now, the sprint begins. Unimpeded by matter, the photon races across the cold, silent vacuum of interplanetary space. It crosses the orbit of Mercury, sweeps past the clouds of Venus, and bridges the 93 million miles to Earth in just 8 minutes and 20 seconds. It plunges through the upper layers of our atmosphere, dodging nitrogen and oxygen molecules until it strikes a green leaf in a forest, driving the chemical engine of photosynthesis, or enters a human eye to paint the image of a bright, sunlit day. Yet even this epic 100,000-year odyssey pales in comparison to the journey of the oldest light in existence. To see the true scale of the photon's reach, we must look beyond our stars and galaxies, all the way back to the dawn of time itself. When astronomers point sensitive microwave telescopes into the darkest, seemingly empty patches of the night sky, where no stars or galaxies exist, they do not find absolute cold or darkness. Instead, they detect a faint, uniform, persistent hiss of electromagnetic radiation bathing the Earth from every direction in the cosmos. This whisper of energy is called the cosmic microwave background radiation, and it is nothing less than the cooling afterglow of the Big Bang. To understand where these ancient photons came from, we must travel back 13,800,000,000 years, to a time when the universe was only 380,000 years old. In that ancient epoch, there were no stars, no planets, and no galaxies. The entire universe was relatively small, unimaginably hot, and filled with a dense, uniform fog of primordial plasma. Just like the core of our Sun today, this early universe was so hot that electrons could not bind to protons to form atoms. They flew free, creating an opaque soup of electrical charges. In this primordial fog, trillions of septillions of high-energy photons were trapped in an eternal random walk. The instant a photon tried to move through space, it bounced off a free electron. Light could not travel any distance at all. The entire cosmos was glowing, blindingly white, and completely opaque. If a human observer could have existed in that early epoch, they would have seen nothing but a wall of brilliant, searing white light pressing against their eyes from every direction. Then, a cosmic transformation occurred. As the universe expanded, it naturally began to cool down. When the age of the cosmos reached roughly 380,000 years, the overall temperature dropped to about 3,000 degrees Celsius. At this precise thermal threshold, the kinetic energy of the particles slowed down enough for the fundamental force of electromagnetism to take control. In a cosmic event known as recombination, the negatively charged free electrons were suddenly captured by the positively charged protons. Together, they formed the very first stable, neutral hydrogen atoms in the history of reality. In a single, sweeping cosmic instant, the fog lifted. As the free electrons were locked away into neat atomic orbits, the obstacles blocking the path of light vanished. The universe became transparent. For the very first time since the creation of the cosmos, light could travel in a straight line without hitting anything. The brilliant, white-hot radiation that had been trapped in the plasma fog was suddenly liberated. A majestic flash of light shot out across the universe in every possible direction simultaneously. Those primordial photons have been flying across the vacuum of space ever since, undisturbed for 13,800,000,000 years. But as they traveled, the universe continued to change around them. According to modern cosmology, space itself is expanding. The physical fabric of the cosmos is stretching out over time, pulling galaxies away from one another. As those ancient white-hot photons flew through this expanding space, their wavelengths were stretched along with the fabric of reality itself. Over 14 billion years of cosmic expansion, the physical distance between the crests of those light waves has been pulled and stretched out by a factor of roughly 1,000. What began as a searing high-energy visible photon has been stretched out and cooled down into a long, low-energy microwave photon, vibrating gently at a temperature of just 2.7 degrees above absolute zero. When you look at the sky today with a radio telescope, you are literally looking backward in time at the physical wall of that ancient clearing fog. Those microwave photons are the oldest possible messengers in the universe. When you tune an old analog television set to an empty channel between stations and see the dancing, chaotic static of black and white snow on the screen, roughly 1% of that electrical flickering is caused by ancient primordial photons from the Big Bang directly striking the antenna of your television. You are watching the literal cooling remnants of creation. As if the photon's ability to bridge time and space were not strange enough, we must now confront one final, unsettling behavior that pushed even Albert Einstein to the brink of disbelief: the quantum connection known as entanglement. In certain specialized subatomic reactions, an atom or a crystal can absorb a single high-energy photon and instantly re-emit two lower-energy photons traveling in opposite directions. Because these two photons were born from the exact same atomic event, they are bound together by the strict mathematical conservation laws of physics. They do not exist as two separate independent particles. They share a single unified quantum wave function. We say that the two photons are entangled. To understand why this is so disturbing, we must introduce a physical property of light called polarization. As a photon travels through space, its electric field vibrates back and forth. The orientation of this vibration is its polarization. A photon might vibrate up and down in a vertical plane, left and right, in a horizontal plane, or at some diagonal angle in between. Polaroid sunglasses work by acting as microscopic picket fences, allowing only vertically polarized photons to pass through while blocking the blinding glare of horizontally polarized sunlight bouncing off water or pavement. For our entangled pair of photons, the rules of quantum creation dictate a strict symmetry. If one photon is measured to have vertical polarization, its twin must instantly possess horizontal polarization, or vice versa. Their states must be complementary. However, according to the standard rules of quantum mechanics, before we measure the photons, neither one of them possesses a definite polarization at all. While they are flying through empty space, their polarizations exist in a state of pure quantum potentiality. Each photon is spinning like a coin in midair, representing an equal probability of being found vertical or horizontal. They are undefined ghosts of chance. Now, let us perform a thought experiment that has been executed in real laboratories around the world. We take our entangled pair of photons and send them flying in opposite directions. We send photon A through a fiber optic cable to an observatory in Hawaii, and we send its twin, photon B, through another cable to an observatory in the Canary Islands, thousands of kilometers away across the globe. While in flight, both photons remain spinning coins of probability, undefined and uncertain. In Hawaii, a physicist sets up a polarizing filter and a detector to catch photon A. At the exact moment the particle strikes the instrument, its quantum wave function collapses. The universe forces the coin to land. The detector clicks, revealing that photon A has solidified into a state of vertical polarization. At that exact identical fraction of a millisecond, thousands of miles away in the Canary Islands, a physicist measures photon B. Without a single microsecond of delay, photon B collapses into a state of horizontal polarization. How did the second photon know what happened to the first? If photon B was genuinely undecided about its orientation while in flight, how did it instantly learn that its twin in Hawaii had been forced into a vertical state? For the Canary Islands photon to adjust its reality to match the Hawaiian photon, an invisible signal would have had to travel between the two observatories across thousands of miles of Earth. But for that signal to arrive instantaneously, it would have to travel faster than the speed of light, violating Einstein's absolute cosmic speed limit. Albert Einstein was deeply offended by this idea. He famously referred to this quantum connection as spooky action at a distance. Einstein argued that quantum mechanics must be incomplete. He believed that the two photons were never spinning coins of probability at all. Instead, he proposed that the photons must have contained hidden internal instructions from the exact moment they separated at the source, like two sealed envelopes containing matching instruction cards that say vertical and horizontal. In Einstein's view, the photons always knew what their states were going to be. Our human ignorance simply made it look like a quantum mystery. For decades, the debate between Einstein's hidden instruction cards and the spooky quantum reality remained a philosophical argument. But in the 1960s, a Northern Irish physicist named John Bell devised a brilliant mathematical theorem, and in the 1980s, a French team led by Alain Aspect, pronounced Alain Aspect, built the ultra-fast optical switches needed to test Bell's theorem in the real world. The experimental results were absolute and undeniable. There were no hidden instruction cards inside the photons. The tests proved conclusively that the properties of the entangled photons are genuinely physically undecided until the exact moment of measurement. When the detector in Hawaii forces photon A to choose a reality, it instantaneously alters the quantum state of photon B across thousands of miles of space without any physical signal, wave, or force passing between them through the intervening vacuum. The photons revealed a truth about our universe that shakes the foundations of human logic. At the quantum level, the universe is non-local. Two particles that have interacted in the past remain part of a single, indivisible mathematical system, regardless of how far apart they fly. Space and separation are, in some deep fundamental sense, an illusion. You cannot touch one piece of an entangled system without instantly sending a ripple through the entire web of reality, defying our classical understanding of distance, separation, and cause and effect. Let us now return from the outer edges of quantum theory and deep time, making our way back to where our journey began. We stand once again on the freezing, wind-swept gravel of the Atacama Desert. The air is still, dry, and cold. The night sky arches overhead, a vast black vault sprinkled with the diamond dust of 1 billion distant stars. We look up, tilt our head toward the zenith, and fix our eyes on Deneb, burning blue-white in the constellation of the Swan. We are no longer innocent observers. We can no longer look at that tiny spark of light and see a simple, continuous ray of illumination. We now know the profound, impossible odyssey that is occurring in the simple, everyday act of seeing. We know that deep inside the core of that supergiant star, 2,600 light-years away, thermonuclear violence forged a tiny disturbance in the electromagnetic field. We know that this packet of energy spent millennia fighting its way through a boiling labyrinth of plasma, bouncing off charged particles in an agonizing random walk until it finally broke free from the star's glowing photosphere. We know that once liberated, this massless ghost leaped across the incomprehensible gulf of interstellar vacuum at 300,000 kilometers per second. While empires rose and crumbled on our little blue planet, while forests grew and mountains eroded beneath the wind, that photon flew on through the dark, never swerving, never losing momentum, and never aging a single fraction of a microsecond. To the particle itself, the journey took no time at all. It bridged the cosmic abyss in a dimensionless instant of absolute now. And now, in this quiet second on the high plateau, that ancient traveler arrives. It pours down through the thin desert air, passes through the pupil of the observer's eye, and terminates its timeless existence by plunging into the retina. Let us zoom in, widening our understanding one final time, to witness the exact subatomic climax of this journey. Embedded inside the specialized photoreceptor cells of the human retina are billions of complex protein molecules called rhodopsin. Locked at the center of each rhodopsin protein sits a tiny, highly specialized chemical molecule called retinal. In its resting state, this retinal molecule is bent and kinked into a rigid, carbon-chained shape. Our traveling photon from Deneb slams into one of these bent retinal molecules. The collision is instantaneous. The photon transfers its entire packet of electromagnetic energy directly into the electron cloud of the molecule, and in that exact fraction of a millisecond, the photon is absorbed and completely destroyed. The timeless ghost vanishes from the universe forever. But its kinetic energy lives on. Absorbing the subatomic punch, the retinal molecule instantly twists. In less than 200 femtoseconds, a timescale so impossibly short that it represents a fraction of a trillionth of a second, the molecule snaps out of its kinked shape and straightens out like a released spring. This violent molecular straightening changes the physical shape of the surrounding protein, kicking off a rapid cascade of chemical reactions inside the retinal cell. Ion channels in the cell membrane snap shut, the voltage across the cell wall drops, and a tiny, crisp electrical impulse is fired out of the base of the cell. This microscopic electrical spark races down the optic nerve, joining millions of other simultaneous pulses, and floods into the visual cortex at the back of the human brain. The brain receives this pattern of electrical signals, interprets the incoming data, and constructs a conscious experience. You see a light. You see a star shining in the dark. Step back now from that single eye on the desert mountain and look at the world around you. Look at the bright, sun-drenched surface of the ocean, where every cresting wave sparkles with blinding brilliance. Look at the soft green glow of a forest floor dappled by afternoon sunlight. Look at the glowing screen of a telephone, the red embers of a dying campfire, the gentle silver illumination of the moon, and the invisible microwave fog that fills every empty corner of the night sky. None of this is static. None of this is a simple, continuous painting of light. We live inside a relentless, vibrating blizzard of quantum energy. Every second of every day, trillions of septillions of massless, timeless packets of electromagnetism are raining down upon our world from the sun, from the distant stars, and from the creation of the cosmos itself. They punch into atoms, drive the chemistry of life, push against the dust of space, and bind the universe together in a web of instant spooky connections that defy human logic. The photon is the ultimate paradox of nature. It is the humblest, most common thing we experience, the medium through which we perceive almost everything we know about the world. Yet, it remains an alien visitor, an entity that obeys rules from a realm beyond our common sense intuition. It reminds us that whenever we look up at the sky, we are not merely watching the universe. We are physically catching its oldest, fastest, and strangest messengers, one timeless particle at a time.